this video, we're going to talk about the general definition of acids and bases and some of their characteristics, as well as the Arrhenius definition of acids and bases. So acids and bases are things that you encounter every day, and they each have some very specific characteristics that are pretty easy to recognize. So acids are very typically sour. So if there's something that, something that you can eat, they will have a sour taste. And if you have ever had citrus fruits, which I'm sure you have, the reason they have that citrus flavor, that sour flavor to them, is because of the citric acid inside of them. Another common acid that's consumed is vinegar. Vinegar has that kind of pickly sour flavor to them due to the acid. And then most acids also have cleaning properties. You can use them to clean various things. Bases, if they're consumable, have a bitter taste. And usually we don't like the things that taste bitter, which is good because there are very few bases that should be consumed. One type that we do consume are called antacids. So these are what you take whenever you have heartburn or an upset stomach. We'll talk more about those later in this chapter. Bases also tend to feel slippery. So if you ever get base on your skin, they have a slick, slippery feeling to them. And then bases are also used in cleaning products. So we're going to have two different definitions of acids and bases. We're going to have the Arrhenius definition, and we will have the Bronsted-Lowry definition. So the first one that we're going to talk about is the Arrhenius definition. So Arrhenius acids are any compound that will produce hydronium ions whenever you place them in water. So hydronium ions have this formula, H3O+, so 3 hydrogens, 1 oxygen, and there's a positive charge. Another way we tend to think about hydronium is H+, so hydrogen ions. These two are used interchangeably, so don't let that confuse you. Hydrogen ions cannot exist in water, so whenever they are in water, what you are actually forming is H3O+. And because we are putting an acid in water to form the hydrogen ion, and by default what we really are forming are the hydronium ions. But if you ever see a reaction written with just H+ rather than H3O+, you can think of it in the same way. So here's an equation showing an acid placed in water. So we have HCl, which is an acid. We place it in water, and what is produced are hydronium ions and chloride ions. This reaction down below shows us how the electrons and atoms are moving around to make and break bonds. So what's happening is this lone pair on water is going to make a new bond with the hydrogen of the acid. Then the electrons that are in the HCl bond are going to go to the chlorine. So what we have as products then are we have H3O+, and one of these bonds is the new bond. And then we also have Cl-. And in the Cl- structure, there are 2 electrons missing. And there should be 8 around that chloride ion. So again, if we look back, our water originally had oxygen bonded to 2 hydrogens. We look at our hydronium ion, we still have oxygen bonded to 2 hydrogens. And then the third hydrogen is added on with a new bond. So we're going to write Arrhenius acid reactions, and here's some guidelines for writing them. There are a lot of words. In the next few slides we'll work through some examples, and sometimes that's easier to see. But what you're going to always do is take the hydrogen ion H+ from the acid, and then you will add it to the water to make hydronium. The rest of the acid, so whatever's left over, will be an anion. That's one of your products along with hydronium. If you have more than 1 hydrogen in the acid, for example H2SO4, then both of them will be removed. And for every hydrogen ion removed, you're going to need 1 molecule of water. And each hydrogen ion and each water molecule is going to make 1 hydronium, and that you'll figure out through balancing. The number of hydrogen ions that you remove are going to tell you what the charge of the anion is. You can also figure out the charge just like we did back in chapter 6 with ionic structures, charge coming from group number, right? But if you take away one hydrogen, you're taking away a positive ion from a neutral, you're going to be left with a -1 ion. If you pull off 2, you're left with a -2 ion, and so on. Basically, you're thinking about how we did dissociation reactions before. Then in the end, you always want to double check and make sure that your reaction is balanced. So here's a generic example. We have the acid HA. A could be whatever anion we want it to be. It's going to react with water, and we will make H2O with an extra hydrogen and a positive charge. So this H2O is coming from the water portion, and then the hydrogen ion is what we're adding on to that. What you're left with then is the A minus back from the HA. So if I re-highlight things here, we've got the A minus, and we have the hydrogen ion. Right? So this H2O plus, H2OH plus is the same thing as H3O plus. So let's practice writing a couple of these. So we've got HBr, which is an acid. We're going to place it in water. And we haven't talked about it yet, but states of matter are important. Your acid is always aqueous. Water is pure water, so it's considered a liquid. So again, what happens is your hydrogen ion from the acid is going to add to the water, and what you will get is H3O plus. Your products are always going to be aqueous because they're in water at this point. Then the leftover part of the acid, the Br, becomes your anion. We removed one H plus, so we're left with a negative. You can also figure that out by looking at the periodic table. Bromine is in group 7, so it's a -1 charge. If we look at the second one here, this time we have 2 hydrogen ions. Right. Again, this is going to be aqueous for the acid. We're going to put it in water, liquid. And it said in the steps in the previous slide, if for every hydrogen ion you have, you're going to need a water molecule. So 2 hydrogens is going to require 2 water molecules. And what we make then are 2 hydronium ions. Then what is left over? We have the SO4. SO4 is sulfate. And you can look at the polyatomic ion table that you have, or we can say, well, you pull 2 positive ions off, so we're left with a -2 charge. If you go back and check, you'll see that this is balanced. We have 2 hydrogens plus another 4 is 6. On the right hand side, we also have 6. And then we have the SO4 and the SO4. To determine if something is an Arrhenius acid just by looking at the formula, it must have a hydrogen atom in the formula. And we talked about whether something is ionic or covalent back in chapter 5 at the very end. And we said hydrogen is a little strange because it could act as a metal if it was with certain things and a non-metal if it was with others. And we said when hydrogen was with something from group 7 or a polyatomic ion, we wanted to consider it ionic. And this is why. Because when we put the hydrogen attached to something from group 7 or hydrogen attached to a polyatomic, it does dissociate like an ionic compound because it's an acid. If hydrogen is attached to an electronegative atom like oxygen or sulfur, then it is a covalent compound, but it's also considered acidic because that hydrogen can be pulled off from there as well. So here we have an example down below. We have this molecule here, the CH3COOH. You notice it's got 2 different hydrogen sections. It has the H3 and the H. Remember, so this is a condensed structure that we talked about last chapter, and the hydrogens are attached to the atom coming before it, So those 3 hydrogens are attached to that carbon. This 1 hydrogen is attached to the oxygen. So if we think back to the previous topics up above, we said if hydrogen is attached to oxygen, we should consider it acidic. Hydrogen attached to carbon is never acidic. So this 1 hydrogen here is your acidic hydrogen. So that 1 hydrogen is going to react with 1 molecule of water to make the H3O+. Just like we saw in the previous reactions. If we pull that H+ off of the acid, we're left with this, the CH3COO-1, as your anion. So here's a couple examples. First, we're going to decide which of the following are Arrhenius acids, and then we will write the Arrhenius acid reaction specifically for H3PO4. So let's look at number 1, HF. So the question is this an Arrhenius acid or not? So we have hydrogen with something from group 7, so this is an acid. The second example, we have hydrogen with PO4. PO4 is a polyatomic, so hydrogen with polyatomic is also an acid. Third example, CH4. Hydrogen on carbon is not an acid. And then this last example, we have these 3 hydrogens on that carbon, these 2 hydrogens on that carbon, this hydrogen on an oxygen. So the 1 hydrogen that is on the oxygen is considered acidic, so this is an acid. Now if we want to write the Arrhenius acid reaction for H3PO4, we're always going to start with the acid. I'll do this up top here. That acid is aqueous. We're going to put it in water, which is a liquid. Just like before, we look for our acidic hydrogens. We have 3 hydrogens attached to PO4. So those 3 hydrogens are going to need to react with 3 waters, and that will make 3 H3O+ hydronium ions. Then if we look, the PO4 is the anion that's left over. So we're going to have PO4. Both of these are aqueous. Then for charge, because we pulled off 3 positive hydrogen ions, we're left with a -3 charge. Again, you can look at the polyatomic ion table to figure that out as well. And notice if you're balancing as we go, meaning every hydrogen is going to need a water and make that many hydroniums, your balancing is done for you in the end. For your Arrhenius bases, these are going to be any compound that produces hydroxide ions, okay, whenever you dissolve them in water. Hydroxide ion we have seen before, OH with a -1 charge. It was one of our polyatomics. So here's an example of an Arrhenius base reaction. We have our sodium hydroxide, which is a base. These will always start off as a solid. Then we place them in water, and we make sodium ions, Na+, and hydroxide ions. Both of these are considered aqueous. This should have a very similar or very familiar look to it. This is the dissociation reaction, like we did back in chapter 6. We have our ionic compound, we put it in water, and it breaks apart into its ions. The reason water is written above the arrow is because it's not actually reacting, but it does have to be present. So here are the steps all written out. Again, probably easier to see by example, but you want to think about what ions your base, which really is just a salt, an ionic compound like we did in chapter 6, what ions does it break into? You're always going to have hydroxide, and then your remaining ion is going to be a cation. To figure out the charge of the cation, you're going to look for your group, and all of these examples will be from either group 1 or 2. Group 1 is always +1, group 2 is always +2. You can also use hydroxide ions, so for every 1 hydroxide you pull off, you're going to be left with a positive charge. If you pull off 2 hydroxides, you're going to be left with a positive 2 charge. The number of hydroxide ions the base in your base must balance with the number that you're writing in your products, and then always double check your balancing at the end. So here's a few examples. Let's do KOH. Again, these start off as a solid. We're going to place them in water. This water does not have to be written across the arrow like this, but we'll do it just for clarification for now. We have OH is our hydroxide. There's one of them, has a -1 charge. Then the the cation that's left over is potassium. It's from group 1, so it's a +1 charge. And both of these products are aqueous. For the second reaction, we have hydroxide again. This time there's 2 of them, so we've got 2 hydroxide. And the cation that's left is beryllium. Beryllium is in group 2, so it's a +2 charge. So to decide if something is an Arrhenius base or not, anything that has hydroxide are Arrhenius bases. Okay. Your ionic compounds have to have a metal. So if they have hydroxide, whatever it's paired with has to be a metal. So kind of a shorthand here is any metal with a hydroxide is going to be an Arrhenius base.